Classical Physics Tutoring, Chapter 1, Section 4, Circular Motion. Now, we deal with the circular motion of a mass. It's a point mass. This is going to be the base for making later the rigid body rotational movement. So, suppose Moon is fine, that the center of gravity becomes the point mass, and the point mass is circling around the Earth. And equation, this motion equation is F equals ma, and if trajectory is simple, r is constant, v is constant, and a is constant, then trajectory equation is going to be r. Then we take a derivative v, and we take a derivative again a. Okay, so what's happening is this, you look at the vector a, it's going to be opposite of r. So we need to have acceleration a this way, and times m is going to be a force. So we can tell this imply gravity force, and it doesn't have to be gravity force. It can be the wire connected and pulling a wire. So the force has to be toward the center of the circle for this kind of trajectory. Okay, so this is the motion, the circular motion of the point mass. Okay, in this point mass, what's happening is we often talk about centripetal force. Centripetal force is some force acting against gravity, and because of this centripetal force, the gravity is cancelled out, and the astronaut on this orbit feel zero gravity. And let's talk about this a little bit. Is there any such a thing, centripetal force? Well, anybody standing on the Earth don't see it. You see only gravity force. Okay, and we talk about this. Gravity force is used, 100% of gravity force is used for changing direction of satellite. So it's not moving toward the Earth, but it's changing the direction. It's, instead of flying off tangent, it's changing. Okay, but the astronaut on the satellite or spaceship feels zero gravity. From his viewpoint, there's no gravity. Why is that? Well, actually, it's just perceived zero gravity. It's exactly the same as when you turn the corner by the car, you feel force acting this way, and the glass cup of water or glass of water, the water moves and sometimes spill on the dashboard. Okay, and you feel the force, this force. Okay, this force actually it's not force, it's inertia. Supposed to go straight, but by external force, okay, you turn the wheel, you change the direction, then you're supposed to go straight, but because you turn, you feel the things moving still straight, and that's the perceived force. So centripetal force is a perceived force. Why you don't perceive that on the spaceship circling around Earth? That's because the trajectory is so large, and you constantly feel inertia going off the tangent. Okay, and this inertia give you perceived feeling that it's cancel out gravity and there's no gravity, zero gravity. Okay, so actually this is totally wrong to call zero gravity. The gravity is there. Then why things float around? Things not floating around. The things like cup you're holding in a spaceship is called tangent by inertia. Okay, but because of the gravity, you're moving toward this way. So you perceive that it's floating, it's staying there. It's falling. Same as exactly the case that if the airplane go down at the acceleration g, you feel zero gravity here because it's perceived. You are falling, airplane is falling, but inside the airplane you feel it's zero gravity. It's the same situation. So there's no such a thing like a zero gravity. Gravity is always there. It's just perceived environment is all the gravity is cancelled out by inertia. Okay, so centrifugal force is a fake force. There's no such a force. It's just convenient to say centrifugal force acting, so you feel like you are floating there. Okay, so typical circular motions, pendulum, the mg is cos theta and the distance is sine theta. Okay, and this force is ma. In the equation, the x distance is sine, and the sine, if theta is small, say this L is very large, right? So it's a theta. So x is actually L theta here, right? Now the acceleration, so we take second derivatives, so m L second derivatives thetas over time equals force mg. But this mg is, this cos is 1 here. Okay, so it's going to be single theta, and this equation, the obvious answer is like a sine omega t, right? Or it could be b sine omega t, either way. So this omega, if you take a derivative twice, then sine change, they match up with theta. We cancel the theta out, so it's going to be omega square is going to be, move L over here, G over L, right? Since omega is 2 pi f frequency, then period is 1 over f equals 2 pi L over G. So the period of pendulum is a function of length and the gravity acceleration. It doesn't matter how heavy the pendulum is. It's not a function of weight, just the length. Okay, so but heavier, the more accurate, because we didn't consider air resistance. and heavier will have a more air resistance. So if you have a pendulum from the ceiling and swinging heavy weight and draw the line along this swinging direction, do you know what's happened? Well, this line stick to the earth, and earth is spinning, right? The earth is spinning, but this pendulum, the motion is not affected by anything. It's just gravity, and on the earth, pendulum is swinging this way, and it's always have the same directional force, even earth is spinning. So you see this line start moving away from this swinging direction, and it's slowly move around and come back to the same position once a day. So this is one of proof that the ground is spinning, earth is spinning. Okay, so that's pendulum. Okay, let's consider how much energy is used for circulating this point mass. Actually, the energy is, kinetic energy is mv square, right? So that's the kinetic energy it's holding. So how much is changed by time? You take a derivative, okay? So dE dt equals mr square omega angular acceleration. Okay, now F is ma, so it's going to be mr angular acceleration. So you equal this, it's going to be m f the dE dt. Oh, m disappear. Rf r omega equals bf. So energy spent seem like the speed times f. That means you have a velocity and f, right? But this angle is a 90 degree. If you do this, it's 0. Okay, so energy spent is 0 for circling around. Okay, now the angular momentum P equals mv, and in this case it's circling around here, so vector is pointing up, equals mr omega n, assuming this is n vector, right? And angular acceleration is f r n, this is wrong, and centripetal force, we know that already, it's going to be mv square r or m r omega square. Okay, this is important. This is important later to come up with the rotational motion's basic equation, the Newton-like equation. Okay, so let's look at let's practice a little bit to see what's happened to this kind of questions. A geostationary satellite, that means it's always above you, it's moved together with Earth, and this is used for the communication, like the TV program or whatever. You set the antenna and pointing to this satellite, because this satellite has, say, Comcast, whatever, and this guy moved together with Earth, so it's always at the same angle. Okay, so you set the satellite on the roof, pointing this satellite, it's moved together with Earth. That's a geostationary satellite. And the geostationary satellite, the movement is 24 hours per circle, right? So the omega is 360 degree divided by 24 hours, which is 60 second, minutes, hour. Okay, that's omega per second. So degree per second. If it's pi radiant, this is 2 pi, so 2 pi per second. So that's the value. Okay, so what is the gravity for this, right? So the gravity is G m r square, right? Now this gravity is equal to what? The convenient force, centripetal force, right? Which is v square r. So we say satellite weight doesn't matter, and gm is going to be r v square, is going to be r omega square. So the r cube is gm over omega square. Omega, we know omega is this one. So the height, okay, this includes the radius of Earth. So if you want to know the height from the ground, you have to subtract the radius of Earth. Is going to be okay, and that's about 42 kilometer above. It's pretty low. Okay, you don't have to even go to 100 kilometers. So that's the way we calculate the satellite height of a geostationary satellite. Let's look at another example of the circular motion. The point mass is Moon, and this is Earth. Okay, so when we have a two gravity point, you can guess somewhere between the gravity is going to balance out here, right? Okay, so we draw the gravity profile. It looks like this. Okay, so here's the gravity balancing point. Okay, now if you are here stationary, it's balancing here, but fact is this whole thing's moving at the omega, the moon's speed. So whatever you have here is going to get the centripetal force. So you need some kind of gravity. So somewhere around here, dynamic system make a balance, because here you get Earth's gravity stronger than Moon, but you have a centripetal force because this is moving together, right? So this point is called L1, Lagrange point 1. Lagrange point 2 is you have two gravity, Earth and Moon, and this one is moving too. So gravity profile like that, and you calculate centrifugal force from the moon distance. There is a balancing point, so that's gonna be L2, Lagrange 2 point. Okay, and other side there is a balancing point here. It's slightly inside the circle because of the moon gravity, and it's moving. So gravity is actually a little stronger than the Earth's gravity because of the moon. So this radius becomes smaller. That's L3 point. In magical point, there is the Lagrange point L4 and L5. So what is it? You have a gravity here and here, two gravity, but you have a centrifugal force because it's also moving along the moon orbit, and that's happened to balance out. That's a Lagrange point L4 and L5. Okay, so those Lagrange point is that you can stably orbit around Earth together with Moon, keeping distance same. So here's the illustration of the centrifugal force and gravity from both E and M. This is L2 point, this is L1 point, L1, L2, L3 point, and we have L4 and L5 point. And if you try to solve this, it's a fifth degree of polynomial, and you cannot solve it by algebra. So you need a computer to get the approximation, and this turned out to be 67,000 kilometers here from the moon. So Earth and Moon 300,000 kilometers away, and the farther down 67,000 kilometers there is a Lagrange 2 point, stable point. Now this is important because 300,000 kilometers away, 67,000 kilometers. In order to keep the balance, we put the satellite here. So stable point, if this distance is pretty much same, this point is same as L2 point, stable point. This is called halo orbit. So China placed the communication satellite here behind the moon. The purpose is to communicate with Earth and the back of the moon, because moon is always facing the same side to the Earth. So how it look like from this communication satellite, a photo was taken, and Earth is here and the moon is here. Okay, so using this communication relay satellite, you can communicate with anybody on the back of the moon. Who is on the back of the moon? Well, China placed the rover there, so that's the way China communicate. The rover on the far side of the moon with Earth. So this halo orbit challenge, probably you should do yourself, but assuming that R are almost same, okay, because this distance is very far compared with this, and satellite is circling around L2 point, so it's going to be slightly inward. This is 67,000 kilometers according to computer's calculation. This is going to be slightly less because we had to keep this distance about this to be stable. So this is like a L2 point collection. The actual shape is a little bit more complicated, something like this, and that's probably China did it using a supercomputer or something. But the simple case, assuming this is circle and the gravity point, you can calculate, see what kind of orbit will be possible, the stable in this. It's a good challenging homework using the circular motion of the point mass, and I let you take this by yourself as a project and think about, see how difficult that is to calculate this kind of things. You need definitely computers, approximation, but it's fun. Okay, I hope you enjoyed this video, and if you like, please subscribe and move on to the next classical physics tutorial.